Okay, so our remote student is named Wade. Do I say hi, Wade?
Hi, Wade.
He's not there live. I'll record the movie and then send it to him. Another thing we can do, if this works out and I don't screw it up too much, is if one of you guys has to miss a lecture, if we're recording it, then you can watch it, because we do cover a lot in 3 hours. So missing it would be painful. Yeah, I taught a microwave engineering class, also from 6 to 9 last spring, and that was pretty brutal if you missed a lecture. But you know, things happen and you have to. So, okay, so here we go. So in this first set of notes, what we're going to do is I'm going to tell you what I think my definition of computational electromagnetics. What is it? And then the boring part. We're going to go through all the rules and regulations, the syllabus kind of stuff. After that, then we're going to start with the class. And I'm going to start off with classifying methods a few different ways. There are a few different ways of classifying them. And what that's going to let you do, hopefully, and maybe not immediately, but by the end of the semester, is given a device or something you want to model, that you'll have a really good idea of what's going to be the best way to do this. And if you come away with nothing else from this course, the ability to do that. To know, okay, I got to model a thin wire dipole. That's clearly method of moments. Or I got to model this dielectric diffraction gradient. That's clearly rigorous coupled wave analysis. I can do that. I want to give you guys that ability. But this is a really good place to start for that. After that, we'll talk about some general topics for computational EM. Then after that, I'm going to take you through an overview of every method and more that we'll learn in this class. Benefits, drawbacks. Try to give you some kind of intuitive feel of how it's working. And at this point, I actually don't expect you guys to get much out of that. But what we're going to do is repeat this at the end of the semester, and after you've felt the pain and coded things and learned a lot, the same set of lecture notes are going to mean a lot more to you. But we'll do it at the beginning, we'll do it at the end. And please just interrupt if you have a question. Don't wait till the end. It's my preferred way. Everybody ready? Okay, what is computational electromagnetics? So by definition, it's just calculating electromagnetic things. But in the 21st century, it definitely implies using a computer. Dim the lights. So it implies using a computer. So we are using a computer to simulate electromagnetic devices. Now, why would you want to do that? Well, one reason is we can't obtain perfect analytical solutions to really anything. There's some very simple canonical cases where we can approximate some things and get some answers that are somewhat useful, but if you have a transmission line that suddenly has a weird geometry like that, you're not going to find analytical solutions to that. In fact, most everything of practical interest today, there really aren't any analytical solutions for. So we have to resort to computation. Another big reason is it's very expensive sometimes to build things and test them. So we can just pretend to build it and test it inside a computer, and we can get things pretty close without building and testing. So it saves a lot of money too. Pretty good? So here's a list of everything we're going to cover this semester. The ones in green are the ones you're actually going to code in MATLAB. So we'll start off with transfer matrix method, then we'll go into Finite-Difference Frequency-Domain. And for those of you that took my computational methods class, there's a lot familiar here, the whole derivative operator thing, that'll crop up here. Then we're going to get into rigorous coupled wave analysis and the plane wave expansion method. And the way I pace the course so that we can also cover the other things is we'll talk through a method, and you'll have everything you'll need to implement it, but it'll take a week or two for you guys to do that. In the meantime, we're going to fill the time with these other methods, and that's how we can get through everything. And it's ordered in a way that you're going to start seeing relationships between them all that probably nobody else in the world can see. To give you an idea, I've been through so many methods, I actually identified a missing one just because I drew a map of the methods and there was a hole in it. I ended up implementing it and publishing that. And it wasn't because I was super smart, it's just there's a hole, there's a method that was missing. And we'll get to that once you guys see some methods. So that's the pace of the course. We're going to talk through a method, and while you're off working on it, we're going to just fill it with other things that we won't implement. But it's nice to know that they're there. They're every bit as valid and powerful methods.
Don't go back.
Oh, yeah. Gosh. Thank you. So we're not going to go back.
It's your last time before.
Yeah, so let me turn to that page. Yeah, I put a lot of thought into that. So, for example, there's one technique on here called Finite-Difference Time-Domain. I actually have a semester-long course on that method. For a lot of these, I just didn't feel I could do justice within one semester. For example, finite element. I think that needs to be another semester-long course. So I didn't see that as a viable way that we could do it in this class and pick up several other methods. Transfer matrix method is really simple, and that's also an entryway into rigorous coupled wave analysis, which is pretty hard to understand, but transfer matrix method is simple, and what you'll see is rigorous coupled wave analysis is just a little generalization to it. So it just has more to do with the flow, and what I want to leave you guys with are the codes that are the most powerful and the simplest to implement. If there was some kind of greatness metric of power over simplicity, the ones I'm teaching here would definitely be it. Also, there's a follow-on course to this that I teach where this is a prerequisite called 21st Century Electromagnetics. Could also just be called Weird Electromagnetics, Weird, Very Advanced Modern Electromagnetic. And you'll need these tools, and I selected those ones specifically to be able to simulate and design things. So the follow-on course is really a device theory class, not really a modeling class, but you need these because the off-the-shelf software can't do some of what you're going to be able to do, which is a great reason. If you're on a job interview, that might be one of the questions, well, why are you doing that when you have this off-the-shelf software? Well, it can't do what you're going to be able to do by the end of this semester, for sure. You're going to have some extremely powerful tools. So why these ones? It's, I think, very nonlinear. I just have all this buzzing in my head. I want to leave you with the most power, simplest codes. What can I teach multiple of? And so out came the ones that are highlighted. So, okay, so grading. Notice this, the homework is 40% of your grade. In my mind, the homework in this class is the class. That's where you're going to be developing your codes and submitting your solutions. So it's darn near half your grade. There's going to be 2 midterm exams worth 15% each. Now, just due to the nature of what we're doing, the tests are going to be take home. So there's going to be nothing that you're going to have to memorize or regurgitate in here in a written test. It's going to be take home. It's going to be implementing codes, and when you have those working, modeling devices. And so there's going to be very little distinction between the homework and the midterms. It's going to be the same format. I'm going to hand it to you. You'll have a week or so to do it. Really the only difference is that in the midterm exams, there won't be a develop a new code. It's going to be taking the ones you should already have working and modeling something new with it. And I can't help you when we call it a test instead of a homework. But the way it's paced, we'll have all the codes working in the homeworks, and then the midterm exam should be real easy, just changing a few numbers up front and simulating something new. Final project, 20% of the grade, and we'll revisit this about halfway through the semester when we're in the swing of things. But what I want you to do is do something a little bit outside of what we do in here. Maybe you implement one of the other methods that we don't implement here. Maybe you take one of the codes that we did write, but you model something that we haven't discussed in the class. So the point is you just take what we talk about here and apply it to something else. And then for the final exam period, you're going to present your project. So no written exam, but you'll hand me a PowerPoint that summarizes your project. So you can work individually, you can work in teams. If you have a team, then we need proportionally more work, right? And then participation, coming to class, that kind of stuff. But the big thing I want to leave you with is remember, homework is 40% of the grades. And in this class, just because of the way it is, it's not an option to miss an assignment because you'll need all of homework number 1 to do homework number 2. You need all of homework number 2 to do homework number 3. It builds. So if you do miss an assignment, you're gonna have to go back and do it anyway to get the rest done. Yeah, onward. So I'm gonna assign the homework on a weekly basis. Keep me informed how you're doing, because I can extend the due dates, but what I recommend doing is getting started on the homeworks pretty much right away, so I can be addressing the problems. If all the problems hit me the day before it's due, then I won't extend it at that point. But if everybody's struggling, everybody's stuck, I really don't have any issues extending the deadlines on homework, but get started early. Okay, cumulative, I already said that. So late homework, the policy is I'll collect the homeworks at the beginning of the lecture, and so for every day late, it's minus 10%, and then 3 days, it's a 0. I won't take it anymore. I mean, I'll take it and grade it, but I'll tell you where you're wrong, but you'll get a 0 on that. The reason for that is I want to get the solutions to you as soon as possible. So if I just said, just hand it to me whenever, then I got to wait until those assignments are in before I can get solutions to you. So, and if you're stuck, the solutions are very, very valuable. And again, homework is 40% of the grade. This class is the homework. That's where you're going to be doing everything. All right, so the format, if you've had me before, it won't be a real surprise. Have a cover page with no work on it. And the purpose of that is privacy. So I don't have to write your grade on the cover. It's hidden underneath. Please put the problems in the proper order. It gets crazy with me grading 16 assignments if they're out of order. So please, problem 1, 2, 3. Try to be neat and well organized. Make it easy for me to follow it, because I want to spend my time helping you on your assignments. If you're going wrong, figuring out what's going wrong, instead of figuring out where your answers are and stuff like that. So try to make your homework easy for me to grade. The biggest thing that helps me is all your codes that you have to submit with the homeworks, put them back in the appendix. Because I can look at your answers up front, and if nothing's wrong, then I won't look at your codes, and I don't want to have to flip through them. But if something is going wrong, then I can go back and start taking a look at your codes and helping you troubleshoot. So please, all the codes go in the appendix. Don't put them interspersed in your homework, so all the answers are up front. Some advice I have is don't do the homeworks for me, do the homeworks for you. Pretend 10 years from now you need to get your way off a desert island by modeling something electromagnetic, and all you have are your homeworks. So you are more than welcome to include extra things, extra notes, a derivation that you want that you think goes. Do whatever you want. This assignment is for you. I need the bare minimum. I need the answers in the codes. But think of these as being for you. These are going to be invaluable for you to go back on and review. How did I do that? Why did I do that? So feel free to put, I don't care if there's extra things in there. So do these for you, not me. Oh yeah, stapled at the upper left corner, no additional binding, because otherwise the stack gets high. So any questions on that? All right. So all exams are take home, that's cool. And it's going to follow the same pace as a homework. In fact, if I didn't tell you it was a test and put test at the top, it would just seem like a homework. Same format, all the rules are the same. The only difference is I can't provide you help. I can clarify what I'm asking, but I can't help you. So, and I forget if I have a slide on help. The best way, if you have, well, I do have a slide later, so we'll get to that. Okay, final project. Another reason that I like doing these final projects is since as we're learning modeling, we tend to have to just simulate kind of boring things, not real interesting, because they'd be a little bit more advanced. And so in some ways, what we do can be a little bit boring, but here you can apply it to some really cool stuff. And I actually suggest if what we're doing in here is related to your research at all, do that. And just have it count for both your research and this class, or something you're really interested in. And that's really neat for the other folks to see. So all you have to submit really is a PowerPoint and present that during the final exam. And how long we have, it's probably a 10 to 15 minute presentation. But if everybody's going to work singly and we have 3 hours, you can do the math, maybe it's going to be a little bit shorter than that. But think about a 10, 15 minute presentation. And I guess really the only rule is that it has to be complete enough that I could take nothing but your PowerPoints and duplicate what you've done. I don't intend on actually doing that, but structure it so that I could. So if you're modeling something, provide all the dimensions, provide all the material properties, all that kind of stuff. Final project is the final exam, no written final exam. That's pretty cool. So there's no tests per se in this class. And I think it's just due to the nature of the material, because you're writing computer programs, and I don't know how you would do that on a written test. So for the projects, you can work alone or in a team. Just it'll be, I would expect proportionally more work out of a team kind of environment. But keep these fun, and if you can, make it related to whatever research or interest you have going on here. Okay, so as far as the MATLAB stuff, definitely use MATLAB. So if you're comfortable in C or Scilab, use MATLAB, because I'm not comfortable in those other languages. So, and the real problem there is if your code's not working, that I may not be able to help you as effectively. And if there's 16 of you and I'm debugging 16 different languages, it gets kind of crazy. So please do it all in MATLAB. And it really is the easiest for what we're doing. It only gets harder in the other languages. I've worked a bit with Python, I've worked a bit with C and Fortran, and this is by far the easiest.
And for the project, it's also MATLAB.
Yeah, so everything, well actually the final project, you could do that in another language, because the final project topic is really up to you. So yeah, absolutely. But as you're getting these new codes working, it helps me if it's in MATLAB, because then we can get it. Once you have a working code, yeah, you can go off and do whatever with it. The other two things that I ask is make sure that the programs follow the block diagrams. One thing you'll notice, if you ever tried to implement a new numerical method, you get some paper and it's massively confusing. There's equations everywhere, and then they just say, that's it, cool, you're on your own. And so what I try to do is I do all that craziness to confuse and torture you guys, but I end it with a block diagram. Do this, then do this, do this, and I think that helps. So in your codes, follow those exactly. So I wrote the codes and actually generated the block diagrams from the code, so they're pretty much exact. Now, is there flexibility of exchanging the order of things? Yeah, absolutely, but I wouldn't recommend doing that until you really get a good understanding of the code. Also, make your code clean. Clean code just runs better. Take my word for it for that. So another thing is I would like your codes, unless I say otherwise, as one single program. And you could argue, well, that's bad programming practice. And it probably is, but it really helps me troubleshoot things. Because if all of you guys break your stuff into different functions, then there's 16 of you, it's going to come to me at 16 different ways, and my life becomes very difficult. So these really aren't long and complicated codes, so just write it as one single document. There's some things that we'll do, we'll break away into separate functions, because we're going to want to test those individually. But put them all in one thing. So follow the block diagram exactly, neat, well organized, don't have junk code in there or anything like that, and keep it in one file.
Is that just for the homework that we turn into you? Because the reason I'm asking is I like to separate my functions and make sure they work, and then I can implement it into the final.
You can do it however you want. Just when you submit it to me, and if I'm helping you troubleshoot a program, just one single, that really helps me a lot. Okay. The other thing, just to make it easier on me, this isn't a hard, fast requirement, but try to use the same variable names I use, because one troubleshooting technique I have, every once in a while I'll get stuck on somebody's code of what's going wrong, and I'll just start copying and pasting my code over top of yours, and suddenly it starts working. Obviously whatever I just pasted in fixed it, and that helps me. So the more similar your codes are to mine, the better. I'm not going to say that's a hard, fast requirement, but it makes my life easier, troubleshooting your codes. So if you need help, make sure that you're following the block diagrams exactly. Make sure your code's neat in a single document, and don't send me your codes at the first sign of trouble. But if you're stuck, send me your code. People have done that in the past. I'm pretty responsive. I usually get back to you in the same day and have your code working. What I normally do is I'll pop open your code and pop open your email, and I'll say, okay, I'm looking at your email, and I go one by one at everything I fix as I fix your codes until I get it working. If you're close enough, I can take it all the way to when it's working. And then I don't send you the fixed code, I send you the comments, and then you can work on it. But I will usually take it until I get it working. I'm pretty good at that, pretty fast. So make sure your code's clean before you send it to me, following the block diagrams. And the reason I say that is I didn't say that when I taught this class before, and I spent 90% of my time just rearranging code to follow the block diagram or cleaning up junk code, and suddenly it works. And the student said, oh, I forgot that line of code was there because half the stuff was commented out. And so clean it up, follow the block diagram, and you actually solve 90% of your own problems that way. But if you're stuck, send your code to me. We'll get it working. So I promise everybody in here is going to have all their codes working by the end of the semester. Definitely committed to that. So just send me your codes. I'll help you get them working. The best way to get a hold of me is my email. My phone dings, I get it right away. I may not be as responsive on weekends and stuff, but otherwise I'm pretty fast, I think. Okay, now on to the good stuff. Any questions on the rules and regulations? I guess the other thing I should have said, it's a graduate class, I don't have to say too much, but please do your own work. There's something to be said for working in groups, but I just don't want to turn it into one person does the work and then everybody else copies. I'm really, really good at the codes. I can see through them and I can tell when that happens. Okay, on to the good stuff. No questions, right? All right. So there's a bunch of different ways to classify methods, and depending what your device is, it could fall in these different categories and point you to different numerical methods. But one way we could talk about low frequency and high frequency methods. Low frequency methods, the device you're modeling is about on the order of a wavelength. And that's actually where we're going to concentrate in this class. This tends to be, well, I think the folks that work over here would argue, but I would say these are the more difficult models because polarization is much more difficult, and we really need to obtain a rigorous solution to Maxwell's equations here. Maxwell's equations, for those of you who don't have an electromagnetics background, that's what governs all of electromagnetics. And so at this scale, we really have to do that. The high frequency methods, your device is huge compared to the wavelength. And there's a lot of approximations that you can make. So this happens with lenses. If you're wearing glasses, that's a high frequency thing. The wavelength of the light is so small compared to those lenses that polarization, things like that become much less important. And in fact, light and radio waves and even sound waves all really behave the same way at that point in the high frequency regime. But in this class, we're going to concentrate here. And we're, for the most part, going to be obtaining rigorous solutions to Maxwell's equations. Rigorous meaning no approximations. Okay, here's the definition of that. So there's three words tossed around a lot. I just did one, rigorous method versus full wave method, and those are different actually, versus a scalar method. Rigorous means we are solving Maxwell's equations as exactly as possible. There's no approximations built in. So if your code had some kind of knob that you could turn, and as you take it up to infinity, if your solution converges exactly to Maxwell's equation, it's called a rigorous method. For those of you that took the computational methods class with me, the step size or the cell size, as we take that to 0, you are actually obtaining rigorous solutions to those one-dimensional differential equations that we were solving. So that's a rigorous method. There are times where full waves, we still have all the vector components of the fields, but we make approximations. Method of moments being the most famous one there. And there's reasons for doing this. Just because it's not rigorous, there's going to be times where this breaks down, but you also buy yourself a lot of efficiency. And sometimes these can do things much faster and handle larger problems than a rigorous solution can. Then, like for the high frequency methods, sometimes we dump in a whole bunch of approximations to the actual physics of the problem, and we would call that a scalar method, or that's probably the most common one. Throw out all vector nature of electromagnetic waves and you'll have a scalar method. And again, there's times we can get very, very accurate results with that. And so there's reasons for doing it. But it's easy to confuse rigorous versus full wave, because full wave still has all the vector nature, but there is somehow approximations built into it. No approximations here, it's just pure Maxwell's equations. Okay, here's 4 thrown at you. We could talk about frequency domain versus time domain methods. So time domain, if you have something that's very transient, if you're interested in modeling pulses, very, very difficult to do that in the frequency domain. So if y'all remember, if you take a very narrow pulse and Fourier transform it, there's a huge frequency spectrum. So if you want something that's very transient, very pulse-like, there's a huge set of frequencies that you have to do with a frequency domain model. That's a whole bunch of simulations that you have to do compared to just one in the time domain. Time domain can also handle nonlinear problems, because nonlinear problems are inherently a time domain thing. A lot of times we can get away without using linear algebra in time domain models, which can slow things down. Most linear algebra techniques scale exponentially. If you double the size of the problem, it suddenly takes 16 times as long to simulate. Whereas time domain, a lot of times if you double the size of the problem, it only doubles the amount of time it takes. And that's a real neat advantage of that. But there's times where this is not good. We want to go frequency domain. The classic one is, and if you take my time domain class, you'll feel this, but if you have a device that's very resonant, so you have a wave that hits a device, it couples in and it just starts bouncing around and it doesn't leave. The more resonant it is, the energy just stays stuck there, and a time domain method, you just got to keep running and running and running and running until finally it leaves, and you can figure out whether it's transmitted or reflected. So for very, very resonant devices, time domain's bad. Doesn't mean it can't do it, it's just not as good. Frequency domain can just blast right through that. So if you're doing very narrow band simulations, things that are highly resonant or have sharp spectral features in their response, you probably want to look at a frequency domain method. Fully numerical versus semi-analytical. Fully numerical will take our governing differential equation that we want to solve, and we'll do whatever approximations we do, but we do it to everything, and then solve it as a big matrix equation. Semi-analytical will take usually 3 parameters, x, y, and z. We'll take x and y and do our numerical approximations, but the z will leave analytical. Now we actually sit down with pencil and paper, solve a differential equation, and plug that back in. But because you have this analytical direction, you can make thicknesses of certain layers whatever you want. It could be picometers to kilometers, and numerically it's free. So it's really neat for modeling long things, semi-analytical methods. So transfer matrix method, rigorous coupled wave analysis, 2 that you'll learn in this class are semi-analytical methods. Real space versus Fourier space. Real space means x, y, and z. Fourier space is a little bit different. In real space, we're going to store the fields at discrete points. So you'll know what the field is at each point. In Fourier space, we're going to store the amplitudes of a whole bunch of plane waves, all at different angles. So rather than storing fields at discrete points, we're going to store amplitudes of a whole bunch of plane waves that are all overlapping. And that's called Fourier space. Again, I don't know if that doesn't make a whole lot of sense to you now, but it will. We'll get into it. Structured versus unstructured grids. For the most part, we're going to be doing all structured grids. This is the easiest thing. So you'll lay out an array of points. They're all equally spaced and distributed, so it's very easy to manipulate that. Unstructured grids, you probably have seen that with finite element methods, little triangles meshed everywhere. That's called an unstructured grid. It's a lot more efficient, but a lot more of a pain to formulate and implement. Everybody good on that? So again, don't worry about absorbing everything. This is the lecture we're going to repeat again at the end, and all of a sudden we, oh, aha, okay, I get it. So don't worry about absorbing everything here. So one question I always get is, hey, can finite difference time domain do this, or can beam propagation method do that? My answer is any method can be made to do anything, period. And I've seen some real ridiculous force fit things. So the real questions are, given a method, what is it best suited to model? And that's what I really want to try in this class to convey to you, what they're best suited to do. But in the end, they can be made to do anything. And if you're curious, if you think a method can't do something, ask me, hey, how could I make this method do this? And I'll try to talk you through that. Or maybe you'll stump me and I won't know. Another confusion in terminology is the word boundary conditions. So in differential equations and electromagnetics, if you've had that, we'll talk about boundary conditions. That's the tangential part of the field is continuous across the interface kind of stuff. But in numerical modeling or computational electromagnetics, if somebody says boundary condition, they could be referring to something completely different and not talking about that. So I like to call what you got from differential equations in your physics classes the physical boundary conditions. The whole tangential field continuous across the interface thing. In modeling, we have what I'll call the numerical boundary conditions, but in the literature it just says boundary conditions, and not to be confused here. What this is, we'll have some device, we have some array, and we're going to be writing a very complex equation one time for every cell in our grid. And so we're going to have pretty routinely 100,000 points, and we're going to write 100,000 equations. Computer is not you. But those equations involve adjacent cells. The question is, if you're at the edge and you need information from a cell on the outside, how do you handle that? You're at the boundary. So that's what a computational person would also call a boundary condition. I'm going to try to call that a numerical boundary condition to differentiate it from physical boundary conditions. But this is a really important thing, how we handle that. Very good? All right, full matrices versus sparse matrices. So we're going to have a grid, and let's say we have a grid that's just 10 points by 10 points. There's a total of 100 points in that grid, right? So if we're going to construct a matrix that's describing just a little 10 by 10 grid, it's actually going to have 100 by 100 elements, because any one element can be coupled to any other element through the whole entire grid. When we're using a technique like finite difference method, we're only going to couple each point to its adjacent point. So it's not really coupled to all the other ones. Methods like that lead to sparse matrices. There's zero everywhere, but just a few numbers in the matrix. And it's very common that they're 99% all zeros. So, and what we'll show later is that it would take terabytes of memory to store that if you stored every single number as double floating point precision. It's much more efficient to only store the elements that are non-zeros. And MATLAB makes that extremely easy. In fact, you just tell it it's a sparse matrix and then forget about it. So one line of code and it does that. But when you're evaluating different algorithms, that can crop up as an advantage or disadvantage. It could be a full matrix where there's actually numbers anywhere. Even methods that give you full matrices tend to still have much more dominant or bigger numbers down this diagonal, but there will be numbers everywhere. Now, usually, if you adopt a method that leads to a full matrix, you won't need as many points. So sparse matrices tend to be very huge. These tend to be smaller. And where the trade-off is, that one becomes more efficient than the other, is something you just kind of have to feel out. So we have methods that solve integral equations and methods that solve differential equations. So think about what's happening if you're integrating. You're summing up everything over the entire device. So every point is coupled to every other point, and the matrix that you're going to come away with is going to be full, simply because every point is coupled to other points. More like finite element or finite differences where the fields locally are just coupled locally. Think about what a derivative is. You don't need information from the outer part of the function. You just need to look real closely, right? So the fields are just coupled to ones adjacent. And so when you're solving differential equations, usually you get sparse matrices. When you're solving integral equations, usually you get full matrices. So why would you ever want to do this? Well, very often it may be full, but it's going to be a heck of a lot smaller. Usually. The little thing is covering, does that say convergence? Yeah. Maybe I'll keep that here over top of the CEM. So this is really, really important. So we're going to have an array, and we're going to give it, say, 100 points by 100 points. And the question comes up, well, how do I know that's enough points? Clearly, the more points you use, the more accurate your answer, but it's going to slow down. And, well, how many points do you use? And I'm going to give you some good rules of thumb on that. But the real answer is you're going to look for something called convergence. You're going to give it a guess. You're going to give it 100 by 100 points. You're going to simulate it. You're going to see the answer. Then you're going to give it 200 points. You're going to simulate it. And you're going to look at the answer. If the answer doesn't change a whole lot, that's called converged. If it changes a lot, okay, well now let's try 300 points, 400 points, and you keep going and you'll see your answer slowly start to converge. So this is very typical. This is something called a rib-loaded waveguide. It's used a lot in integrated optics. And what I'm doing here is, this is essentially the number of points in the grid along the horizontal axis. So as we move out, we're going more and more points in the grid. So we're going to resolve the field much more accurately. You can see a nice smooth field here compared to here where it's all pixelated. Over here, it runs really fast, but we may not get as accurate an answer. Over here, it's going to be very accurate, but probably run real slow. So in this case, maybe we're interested in something called the effective refractive index. I wouldn't worry about a whole lot about what that is, but watch its behavior as you add more and more points to the grid. It bounces around, but then starts to converge a little bit, right? And so I would look at this and say, you know, maybe somewhere lambda over 15, however many points that is, that's it. That's where this method converges.
Are all of these methods convergent? Or are they
Yeah, they all do that. Now some methods at some point explode again, and you just got to handle that. The worst method I ever implemented is something called the string method. It's actually not modeling electromagnetics at all, but it's an inherently unstable method. All the methods we're going to do here are called inherently stable. So in other words, as long as you don't screw up, you'll see something like that. But this string method, oh man, it's inherently unstable. And everything you do to make it stable also makes it less accurate. But this is a pretty typical convergence plot. In fact, it's probably one of the more well-behaved. Usually they jump around and then kind of settle in. So more accurate, but longer runtime. And it's kind of up to you to figure out where you need to be. But you're always looking for a convergence. In fact, the off-the-shelf software builds this in. It usually models things several times. It models it once. It looks at where the fields are varying most abruptly. Then it goes and uses a denser mesh around those points. And it just keeps going and adding more points automatically built in. So the codes in this class aren't going to be that sophisticated. You're going to run it. You're going to add more points. You're going to run it again until your answer doesn't change a whole lot. But that's going to be standard practice for you. Always looking for convergence. Okay, so I have 3 golden rules for modeling. The first one is that every number in your model should be 1. As soon as they deviate from 1, you lose accuracy because of rounding. So for example, 1.23456 plus 0.01234567. If we add that, we're actually losing 2 digits of precision. And that's bad, right? So we actually want to add things that are as similar as possible. So you want every number in your code to be 1. So what this means is you normalize the heck out of everything. A good example of this is in electromagnetics. The electric and magnetic fields are about 3 orders of magnitude different because they're related through something called the impedance. So right away, every time you do something that involves an electric and magnetic field, you're going to be losing 2 digits, 3 digits of accuracy. So what's very common is that we scale either E or H to make them the same order of magnitude and you don't lose that precision. Other things that are very common, wavelength is going to be a very fundamental thing to us. We'll normalize it by dividing by some dimension. So in fact, in our codes, wavelength won't have units anymore. And it's going to be in the order of 1. Then we can also normalize our grid coordinates. So if we think we've normalized enough, we're just going to normalize more. You just keep doing that until everything it's as close to the value of 1 as possible. Make sense? Golden rule number 2, never perform any calculations. My gosh, that is the worst thing you can do, is calculate something, because that's when all the errors happen. So why does it happen? Because of all the rounding and stuff like that. So the mode to get yourself in is that you're going to take all your stuff as far as you can on pencil and paper and think of like getting into the code and out just as quickly as possible. Be really paranoid about touching the data in the computer. And if you have that paranoia, I think you'll write some pretty robust codes. Another way this manifests itself is, let's say you're calculating some kind of radius. So r equals the square root of x squared plus y squared. And then you're going to calculate some kind of Gaussian, where you're going to use r squared in here. Well, you've just taken the square root and then squared it again. So that's 2 mathematical operations where that's introducing error that you don't have to do. So the answer is, don't square root it, and then don't square it here. We've eliminated 2 mathematical operations and did the same thing. So we'll do things like this all the time, and we'll figure out how to not do a calculation if we can. So be very paranoid about calculating stuff. It's the worst thing you can do. Okay, and rule number 3 is to follow rules 1 and 2. If you do that and have a healthy level of paranoia, you're going to write some very, very robust codes. And I think all the codes in this class you're going to find to be very, very robust. So robust, in fact, that you can even get away with some sloppiness and it still works pretty well. Okay. Everybody good with that? So nobody's going to calculate anything, right? All right, here we go. Overview of the methods. So the first method that we're actually going to talk about in this class is something called the transfer matrix method. And I envision it this way. So you're going to have some device that is of infinite extent in this plane, but is divided into layers going this way. So the approximation is that is of infinite extent. And so we're going to excite it, and it's going to also reflect some of the fields, and there's going to be some distribution of the fields at that first interface. Through our magic mumbo jumbo, we're going to come up with a matrix that we call a transfer matrix. And if we take the field here and multiply it by T1, we'll get the field there. So it kind of transfers it from interface to interface. We do it again, we get the field here. We do it again, we get the field here. And now we know what's been transmitted and reflected. We've modeled the device with these transfer matrices. So that's it. Any questions on that? This is the fastest of the methods that we're going to model, but there's clearly a limitation. That the assumption is that these slabs are of infinite extent. Well, what if it's not? Well, this method just can't handle that. So you'll see this a lot in something called thin film optical filters. You want as much light as possible, like take your camera on your cell phone. It's a little tiny camera, so there's not a whole lot of light going in. So what light does go in, they really want to get to the detector. So there's actually a lot of thin film optics in here where they're preventing reflections. And they model and design these things with transfer matrix method. So this lens, I don't know, I'll call it a ½ centimeter wide, but the wavelength is like 500 nanometers. So this lens is huge compared to the wavelength, so it's a really good approximation that these layers are of infinite extent. So a lot of times that is really good. And other times, I'll even start here. Even if this is not a good approximation, I'll start here, get a rough crude answer, then move it to the next level, things that can account for that. and kind of work up in complexity. Now, does that give you a pretty good feel of transfer matrix method? Okay. And that's the first one we'll learn in this class. Okay, so I just pretty much talked through all the benefits and drawbacks. It's really fast, very, very efficient. It is rigorous if that approximation of being of infinite extent is valid for you. So you get a rigorous solution to the differential equation. As is all the methods we'll develop, it's unconditionally stable. So that only means it's only going to explode if you screw up, if you made a mistake somewhere. Very robust, very simple to implement. The main drawbacks is it's limited in the geometries that it can model. So, because these layers have to be of infinite extent. The next one we're going to learn is something called Finite-Difference Frequency-Domain. And this is actually one of my favorite methods. This is probably the simplest of the methods to implement, and it's incredibly powerful and can do almost anything. In my research group here, we have almost every numerical method there is. We have access to it. We have access to all the commercial software that we could ever use, and we routinely go back to this for doing things. It's just great for field visualization. It's just a great, great method. And if you took the computational methods class with me, you got a little bit of taste of what that's going to feel like when we did the transmission line stuff. But here we're going to be solving waves bouncing around instead of transmission lines. But for those of you that had the class, this is going to make sense. If you haven't, don't worry about it. But we have Maxwell's equations. We have derivatives in here. So we're going to jump immediately to matrix form. And then we're going to collect all these into a single matrix equation that we solve, and then we'll have the fields. So we're going to take some area that we want to model over. We're going to represent it as a whole bunch of points, and that's what we're going to process, that little set of points. So great, great technique. Of course, I just talked through all the benefits and drawbacks. But that's probably my favorite of all the techniques. It's just so simple and so powerful at the same time. Then that's a frequency domain model. Obviously, it's in the name. It has a time domain brother. And this method is, if nothing else can do it, people go to finite difference time domain. This is probably the most common algorithm to be running on big computer clusters and supercomputers. It accommodates parallel processing really well. But it's almost exactly like finite difference frequency domain, except you're solving it in the time domain. And the quick hand-waving argument how this works is you'll have one of Maxwell's equations, you'll calculate the curl of the electric field, and that tells you how much your B field is going to change. You end up updating your B field based on the curl of E. Then given this new B field, you'll calculate the H field. Then you'll calculate the curl of the H field and update the D field. And based on the D field, you calculate the E field. Then based on the new E field, you update the B field, and this just runs in this serial manner, and it steps through time that way. And that's finite difference time domain. It's neat because it creates little movies. You can watch the waves move around. This is the method I have a semester-long course on. So some of you took that already that are in here. So I think that's a pretty neat course. We'll spend one lecture on this. Obviously, we can't do it justice, but I'll do my best. So, but being time domain, the primary benefit in my mind to this is that it's not based on any kind of linear algebra. We're not using matrices to solve this. So it scales very well. That means so if we double the size of the device we're simulating, it only doubles the number of computations. So they call that scaling linearly. And that's actually very unusual. Most methods, if you double the size, you quadruple or 16 times the number of computations it takes to solve. So this is very unusual from that perspective. But also being a time domain method, it's better for nonlinear devices. It's better for very broadband simulations, but horrible for really resonant things. And one of the assignments I give in the finite difference time domain class is I give you something very resonant to simulate, and you watch the wave hit it, it gets stuck in the thing, and it just bounces. And literally, your program will be running for hours until this energy finally leaves, either as transmitted or reflected energy. So that's a real drawback of a time domain method. Then there's something called beam propagation method. And I talk about this because it's, once we get some fundamentals in how I implement finite difference method, it's actually pretty easy to understand and implement. It's not used a whole lot anymore. It was used in the older days where computers were less efficient, and it's mostly just a forward propagating thing. It really can't account for any backward reflected energy. So here's a big dielectric blob. The wave hits it. Notice nothing's getting reflected. Clearly that's not physical reality. A lot of things can still be modeled somewhat accurately that way, but you solve it one slice at a time. So you're not solving this all simultaneously, you're going one slice at a time. So numerically it's a bit more efficient. But since you're doing that, it doesn't account for backward energy. Then there's a technique called method of lines. And this is what I was talking about before, a semi-analytical method. And the way this works is we're going to have some device, and typically we use periodic boundary conditions around these edges. So imagine having an array of those unit cells. I probably should have drawn that somewhere, but I didn't. So, but you'll notice at each of these layers it's uniform in Z, this up-down direction, but it could be anything in the cross-section. So you'll break down your device into layers that are all uniform in Z, but can be anything in this direction. Then what you do is you look at this cross-section, and we'll calculate what electromagnetic modes can exist in that cross-section. And you get two pieces of information doing that. You get what the mode looks like, and you also get its propagation constant, which tells you essentially how fast it travels through the layer. So with those two pieces of information, we can now analytically propagate these modes through the entire layer, just with one analytical equation. So this can be miles long, or it could be nanometers thick, and it's the same numerically at that point. So we know the modes, we propagate them analytically. We can do that within the layers, but then at the interfaces, this is where we're matching physical boundary conditions. We'll match the tangential field. And essentially, we connect all of these, and now we describe propagation through the whole thing. And we'll use things called scattering matrices to connect the different layers. But that's method of lines. So the mathematical definition, if you read about it, they say you discretize all independent variables but one and solve the third one analytically. So what's meaning is we're doing a numerical solution here, x and y, so they become discretized, but z stays analytical. And we are literally going to solve analytically a differential equation in the z direction to do that. That's the best I can do with an intuitive feel of what method of lines is. Then there's rigorous coupled wave analysis. We're actually not going to implement method of lines. We're going to implement a different flavor of it called rigorous coupled wave analysis. And this really is the method of lines, except the technique we use to discretize x and y is a Fourier transform. So we're actually in Fourier space here, which means instead of really seeing what the fields look like, we're decomposing the field into a bunch of plane waves, all at different angles. And we're going to know the amplitudes of each of those. And while I've drawn these in physically separate spots, they're actually all overlapping. I just drew them separate so you can see them all. So in each layer, we're decomposing field into these plane waves, all at these different angles. And remember, hopefully somewhere along the way, you took a square wave function and you Fourier transformed it into a series of sines and cosines. And it probably only took 6 or 7 sines and cosines before it started to look pretty square. So we only need 6 or 7 numbers then to describe that. If you were to describe a square in real space, it's going to take like 20 to 40 points before it really starts to look just as square as it did in Fourier space. So it's a lot more efficient to analyze things in Fourier space. It does have some problems. Remember Gibbs phenomenon? You know what that is? If you Fourier transform something, at the discontinuities you get a spike. when you reconstruct it. Y'all seen that? So it's something that looks like this. So if you decompose that into a Fourier series and add together, I don't know, 10 components or so, and then add those together, you actually get this. And these spikes are called Gibbs phenomenon. And in fact, the magnitude of those spikes does not go away. You could have 1,000 sines and cosines, and those spikes are there with the same magnitude. They do get thinner, so electromagnetically they get less significant, but they're there. And this is the main problem with the Fourier space method. And Gibbs phenomenon is more severe the higher that jump. So that means if you're going from very low to very high dielectric constant things, or you have metals that are very extreme values, so jumps between extreme values really bog down this method. So it's really only good for doing things with like glass that have a low dielectric constant, but there's a lot interesting that uses just dielectrics. But rigorous coupled wave analysis is the method of lines. It's just now in Fourier space. We have plane waves now instead of knowing the field at each point. And we'll implement this. Then there's a technique. It's actually similar to rigorous coupled wave analysis. We're going to do this one before we do rigorous coupled wave analysis. It's also a Fourier space technique, but we're actually going to decompose it into plane waves in all possible directions. There's no analytical direction anymore. It's a Fourier transform in all possible directions. And what we end up doing is calculating electromagnetic modes in periodic structures. And what we'll use this for, and what it is used primarily for, is calculating band diagrams. If you've ever taken any semiconductor courses, you probably have seen or at least heard of band diagrams. Those same things apply to electromagnetics. Instead of talking about electrons going through potential cycles, now we have an electromagnetic wave going through changes in the refractive index and stuff. And we get bands. And this is probably the most popular technique for calculating those. And in fact, it was originally invented to calculate bands of semiconductors. So it's the same technique, just modified for Maxwell's equations. So the semi-analytical methods have the benefit that they have this one direction that can be any thickness. And they're very, very efficient for things that are described that are, complex in this Z direction. If there's a lot of variations in the Z, a lot of different layers, the fully numerical methods tend to be a little bit more efficient, like Finite-Difference Frequency-Domain. But there is benefits to being able to handle one little layer at a time. So what if we wanted a method that was kind of both, that you could step through one slice at a time, but was still rigorous and still kind of carried the benefits of the semi-analyticals plus the benefits of the fully numerical. And that's where this slice absorption method came in. This is actually one that I developed. We're not going to implement it, but I'll talk about it and how that works. I actually did it because I was motivated, because somebody told me it couldn't be done. There's nothing more motivating to me than somebody telling me it can't be done. Finite element, you probably have all at least have heard of this. And there's actually an additional step in here over the other methods, because there's this whole meshing thing. You have your device, and the first thing you have to do is mesh it. Now you describe it with all these triangles. And in fact, many times that's the slowest part, is just the meshing, figuring out where all the triangles have to go. Once you have that, then you go ahead and you build your matrices and you solve them and you get the answer to the problem. So that's finite element, and we'll talk a little bit about that. We're certainly not gonna implement it. And at some point, I may develop a semester-long course on all the variational methods, finite element, method of moments. They all kind of fall under variational methods. And you'll know more about what that means when we get to it. The benefit of this, though, really comes from the meshing. We can real easily, if there's something abrupt happening here, we can real easily reduce the size of the triangles there to resolve that and leave the rest really coarse. very, very efficient at doing that. That buys you a lot of efficiency, but it also buys you a lot more headaches in the formulation and implementation that just aren't there for things like finite differences. Finite differences, we'd have to make the whole grid finer, even if there's just some little booger happening here. We have to make the whole mesh finer. And there's fixes to that, but then the finite differences start looking more like the finite elements. Remember, I told you there's not really finite difference and finite elements. There's actually this blur of methods in between. We can develop finite difference method that has an unstructured grid like this. And we can also put finite elements on a structured grid. So it really is blurred. Method of moments. So this is based on a technique called the Galerkin method. And again, we're not going to go into a lot of details of this, but you'll see the method of moments a lot with metallic structures, modeling metallic things. Thin wire antennas, horn antennas, parabolic dish antennas, very large things. If they're just metallic and they're large, this is a great, great technique. The problem with it is it leads to a full matrix because you're solving an integral equation now instead of a differential equation. But you can get away with a lot fewer points. And we'll talk about this later on in the semester too, so you get a better feel for it. Boundary element method. This is very similar to finite element, but finite element has to put triangles throughout the entire volume of the device. Boundary element just has to mesh the surfaces. You don't have to fill in what's on the inside or the outside. So there's fewer triangles that you have to solve, but this also leads to a full matrix. Fewer triangles, smaller matrices, but it's full. Whereas if you did this with finite element, you'd need a lot more triangles, but the matrices are going to be sparse. So you tend to use boundary element when what you're modeling is more efficiently described by surfaces. The classic example is a sphere that has very little surface area compared to its volume. That's why they store cryogenic things in round tubs. It loses less heat. So if you were to model a sphere, boundary element is ideal for that because very few elements around the surface. Whereas finite element, you'd have to resolve it throughout the volume.